The concept of the nuclear-powered surface combatant evokes the naval competition of the Cold War, when the United States Navy sought to leverage the limitless endurance of nuclear power to project power without the friction of conventional logistics. In the later half of the 20th century, the US Navy had operated a significant number of nuclear-powered cruisers, demonstrating unprecedented operational freedom during high-speed, unrefueled global transit. However, despite the allure of infinite range, the high financial cost, complex maintenance cycles, and rigid crewing requirements ultimately led to the retirement of the entire fleet in favor of conventional gas turbine propulsion. Today, as the strategic focus shifts to the Pacific Theater and its vast distances, debates have re-emerged over whether the US Navy should bring back nuclear-powered surface combatants. Assessing the merits of this requires a consideration between their unmatched endurance and capabilities on the one hand and their high cost on the other. Between the late 1950s and the 1980s, the United States Navy constructed 9 nuclear-powered cruisers across 4 distinct classes. These included the pioneering USS Long Beach, the Bainbridge, the Truxtun, the 2 ships of the California class, and the 4 Virginia classes. These vessels were designated as nuclear-guided missile cruisers, or CGNs, and they were designed to operate alongside the newly emerging nuclear-powered aircraft carriers. A key demonstration of their capability occurred in 1964 during Operation Sea Orbit, when an all-nuclear task force consisting of the first-ever nuclear aircraft carrier, the USS Enterprise, the CGN USS Long Beach, and USS Bainbridge completed a 49,190-kilometer unrefueled cruise around the world in just 65 days. This historic voyage proved that a nuclear-powered surface group could transit to any global flashpoints at high speed without the need to slow down or detour for marine fuel replenishment. However, despite this unmatched operational freedom, the experiment came to an end in 1999 when the US Navy retired its final nuclear cruiser, the USS South Carolina, opting instead for a surface fleet entirely propelled by conventional gas turbines. In the decades since, the emergence of the Western Pacific as a strategic hotspot has led naval planners to question whether to bring back nuclear-powered surface combatants. Assessing the merits of reintroducing these vessels requires a careful examination of the key advantages and the equally serious drawbacks posed by nuclear cruisers. The foremost advantage of a nuclear-powered cruiser is its virtually limitless tactical range and sustained high speed. Unlike conventional vessels powered by marine gas turbines or diesel engines, a nuclear cruiser can maintain its maximum speed of over 30 knots indefinitely. This allows the ship to outrun severe weather and maintain high speeds while executing complex, evasive maneuvers in high-stress environments. In a modern conflict across the vast expanses of the Pacific Ocean, where the distance between major logistics hubs can span thousands of kilometers, the ability to transit at maximum speed without depleting fuel reserves is a massive operational asset. Furthermore, a nuclear cruiser completely removes itself from the marine fuel replenishment pipeline. In a carrier strike group, or CSG, the conventional escort cruisers and destroyers burn massive quantities of fuel when keeping pace with a nuclear aircraft carrier at high speeds. Eliminating this requirement for the escorts drastically reduces the burden on the fleet of replenishment oilers. These supply ships are slow, vulnerable, and would be prime targets for adversary submarines and long-range missiles in a peer conflict. By removing the need for marine propulsion fuel, a nuclear cruiser makes the entire strike group far less vulnerable to interdiction targeting its logistical tail. Beyond propulsion endurance, the modern maritime environment introduces a new argument for nuclear power, which is the abundant electrical power margin provided by a naval reactor. Modern naval warfare is increasingly defined by very power-hungry electronics and sensor suites, such as the AN/SPY-6 Active Electronically Scanned Array, or ASAR radar, which presumably would be used on any future large surface combatants. Looking towards the future, the US Navy is actively developing and deploying directed energy weapons, including high-energy lasers and high-power microwave systems designed to counter swarm attacks and incoming anti-ship cruise missiles. These systems, along with potential electromagnetic railguns, require immense sharp bursts of electrical energy and the requisite cooling infrastructure. A nuclear reactor offers a continuous and massive thermal and electrical output that can easily satisfy the power requirements of these advanced weapon systems, without degrading the ship's propulsion capabilities or draining its fuel reserves. The cooling system on nuclear reactors is already mature by and large, although the cooling for the radar systems themselves remain a complex issue. Anyway, the point is that the nuclear reactor provides a large and instantaneous capability to generate electricity for the onboard combat systems and the hotel load. Despite these compelling operational advantages, the disadvantages of nuclear-powered surface combatants are structural and severe. The question is ultimately whether these drawbacks are prohibitive. The most prominent disadvantage is the immense life cycle cost associated with naval nuclear propulsion. Nuclear ships are extraordinarily expensive to design, construct, operate, and eventually decommission. The initial procurement cost of a nuclear reactor core, along with its heavy radiation shielding and specialized containment structures, significantly inflates the ship's overall construction cost relative to conventional alternatives, like the Bainbridge Flight 3. To derive a semi-credible estimate for a modern nuclear cruiser, we employ an estimation based on the cost changes observed historically during the US Navy's transition from conventional to nuclear-powered aircraft carriers. During that shift, moving from the oil-fired Kitty Hawk class to the nuclear-powered Nimitz class, procurement cost experienced a large nuclear premium, generally reflecting a multiplier for the nuclear carrier of around 1.7 to 1.9 times the conventionally powered Kitty Hawk. If we anchor our baseline to the current cost of an Bainbridge Flight 3 destroyer, averaging roughly $2.5 billion, and apply a conservative multiplier of 1.8 to account for the nuclear premium, which includes shipyard infrastructure and the complex engineering overhead required for nuclear naval propulsion, we arrive at an estimated unit cost of $4.5 billion for the hypothetical nuclear cruiser. While this methodology is undeniably reductive and fails to account for things like regulatory compliance, nuclear material handling, and of course the lack of a current nuclear surface combatants production line for direct comparison, it remains the most viable and the best fit proxy available. In the absence of a modern nuclear cruiser program, this ratio offers the most grounded mechanism to quantify the fiscal cost of returning to a nuclear-powered surface fleet. Essentially, for the price tag of one nuclear cruiser, you should be able to buy 2 of the conventional Bainbridges. Operating costs are similarly elevated compared to conventional equivalents. A nuclear power plant requires a large, highly specialized engineering department filled with qualified officers and enlisted personnel who demand extensive training and higher retention bonuses. Furthermore, midlife modernization for a nuclear vessel is a deeply complex affair. A nuclear cruiser requires a complex, multi-year midlife refueling and complex overhaul, or RCOH. This process takes the vessel completely out of the operational pool for years at a time, drastically reducing its availability to the fleet over its total lifespan. Finally, the decommissioning process is an environmental and financial burden, requiring the careful hull cutting and disposal of the nuclear reactor compartments at specialized facilities. And the US Navy has a lot of disposal of decommissioned warship it needs to do over the coming decade already, including nuclear warships. Another critical disadvantage is that a nuclear cruiser cannot truly achieve complete logistical independence because of the persistence of other human and material requirements. While the reactor may run for 20 years without refueling, the ship will still run out of food for its crew within 30 to 45 days. It will also rapidly deplete its supply of aviation fuel for its embarked MH-60 helicopters and organic unmanned aerial vehicles during high-tempo operations. Most importantly, a surface combatant in a high-intensity conflict is fundamentally limited by its ammunition capacity. A modern cruiser relies on its vertical launch system, or VLS cells, to fire defensive and offensive missiles. Once these VLS cells are empty, the ship must retreat to a secure pier to crane-load new missiles, as reliable open-ocean VLS replenishment remains for the most part an unresolved technical challenge. Therefore, a nuclear cruiser remains tethered to the same logistical realities as a conventional ship. It cannot stay in the fight indefinitely just because its propellers can turn forever. Additionally, nuclear-powered vessels face rigid geopolitical and regulatory constraints. Many allied nations maintain strict nuclear-free port policies, which would prevent a nuclear cruiser from pulling into critical regional hubs for crew rest or emergency repairs, thereby limiting operational flexibility. When balancing these factors, we must look at the overall needs of the fleet rather than the performance of a single ship in isolation. The decisive factor that tips the balance against reintroducing nuclear cruisers is the critical requirements for fleet mass and VLS cell numbers. In the contemporary security environment, the primary challenge facing the US Navy is a serious inadequacy of warship hulls and vertical launch cells and shipbuilding capacity relative to the rapidly expanding fleet of its competitors. Naval warfare against a peer adversary would be an attrition conflict decided by the volume of firepower and the number of combatants the fleet can present. As we have estimated, building a nuclear cruiser today would introduce a cost premium of roughly 70 to 100% over a high-end conventional vessel, even holding most other capabilities the same. For the price of 2 nuclear cruisers, the US Navy would have to sacrifice 3 or 4 conventional destroyers. This trade-off directly degrades the total firepower of the fleet, as 3 or 4 conventional destroyers provide far more VLS cells and can cover more geographic areas than 2 nuclear cruisers. Furthermore, the domestic industrial base is facing unprecedented capacity constraints. The only American shipyards capable of handling naval nuclear propulsion, Huntington Ingalls Industries in Newport News, and General Dynamics electric boats are already overwhelmed trying to meet production schedules for the Virginia-class attack submarines, the Columbia-class ballistic missile submarines, and the Gerald R. Ford-class aircraft carriers. Introducing a new nuclear surface combatants program into this fragile ecosystem would trigger a further shortage for skilled labor and materials, ultimately delaying the construction of the submarine fleet, which remains the primary capability advantage for the US Navy. Fortunately, the US Navy does not need to accept the financial and industrial burdens of nuclear power to achieve the high energy capabilities it requires for future weapons. The emergence of integrated power systems and hybrid electric propulsion offers a practical alternative. In a modern integrated power architecture, such as the one planned for the next generation destroyer program known as DDG-X, large gas turbines generate electricity for a shared power pool. This electricity can be dynamically shifted between driving the electric motors and powering the megawatt-class radars or directed energy weapons. This approach provides to an extent the abundant power margin and importantly the surge capacity of a nuclear reactor, without any of the associated crewing challenges, shipyard bottlenecks, diplomatic restrictions, or life cycle cost. In conclusion, while the historic vision of an all-nuclear surface fleet remains an elegant conceptual ideal, it is fundamentally mismatched with the fiscal and industrial realities for the United States of the 2020s. The US Navy must be large enough to threaten peer competitors across the global naval theaters, and heavily armed enough to sustain a high-intensity missile drill. Reintroducing nuclear-powered cruisers would yield a surface fleet that is precisely the opposite: overly expensive, fewer in number, and starved of missiles. The operational flexibility of infinite range cannot really compensate for the loss of raw combat mass. Therefore, the US Navy should firmly reject the reintroduction of nuclear-powered cruisers, focusing instead on the production of conventionally powered, capable surface combatants equipped with integrated electric power systems.